Question 1. The atomic mass of oxygen is 16. Hence, the electrochemical equivalent of oxygen in kg per coulomb is. We give 4 options over here. Electrochemical equivalent is given as equivalent weight upon 96,500. So, equivalent weight of oxygen is given as equal to atomic weight upon valency, which is equal to 16 by 2, which we get as 8 grams, which can be converted into kilo, that is 8 into 10 raised to minus 3 kg. So the electrochemical weight the electrochemical equivalent is equal to 8 into 10 raised to minus 3 upon 96,500 kg per coulomb, which is, we see our answer matches with option A. Therefore, option A is the correct answer. Question 2. When 48,250 coulomb of electricity is passed through an aqueous solution of nickel iodine, atomic mass of nickel is given as 58.8. The mass of a nickel metal deposit would be dash. We're given 4 options over here. So nickel, to form a nickel of 1, we need 2 of electrons, which is in aqueous position, gives us nickel. So 2 Faraday, that is 2 into 96,500 coulomb of charge is required to deposit 1 mole, that is 58.8 gram of nickel. So 48,250 coulomb of electricity will deposit. Therefore, we can get that as 48,250 into 58.8 upon 2 into 96,500, which is equal to 14.7 grams of nickel, which is, we see our answer matches with option B. Therefore, option B is the correct answer. Question 3. Mass of a copper deposited by the passage of 2 ampere of current for 965 seconds through 2 mole of solution of copper sulfate, where its atomic mass of copper is given as 63.5. We have given 4 options over here. So we have I equal to 2 ampere and time, that is T equal to 965 seconds. We have W is equal to Z into I into T. But Z we have equal to E upon 96,500, where E is equivalent to mass of a copper. Therefore, we have E equal to 63.5 upon 2. In copper sulfate, copper is in +2 states. So substituting, we get W equal to 63.5 upon 2 into 2 into 965 upon 96,500, which is equal to 0.635 grams, which is, we see our answer B is the correct answer. Question 4. Time required to deposit 90 gram of aluminum from an electrolytic cell containing aluminum oxide by a current of 965 ampere is given. We are given 4 options, where atomic mass of aluminum is given as 27. So we have W equal to 90 grams and we have I equal to 965 ampere. We have W is equal to ZIT, where we can find T, which is equal to Z W upon ZI, where Z is equal to equivalent mass upon 96,500. For aluminium, equivalent mass is given as 27 upon 3. In aluminum oxide, aluminium is in plus 3 state. So therefore we substitute, we get Z is equal to 27 upon 3 into 96,500. Therefore we substitute this Z in the formula of T, which is equal to W upon Zi, where we get T equal to 90 into 3 into 96,500 upon 27 into 965, which is equal to, when we solve this, we get 1000 seconds, which is approximately equal to 16 minutes 4 seconds, where we see our answer matches with option B. Therefore option answer B is the correct answer. Please note that when we solve this, we get as 40 seconds, that is 16 minutes 40 seconds, which is option B. So option B is the correct answer. Question 5. Passage of 96,500 coulomb of electricity liberates dash liter of O2 at NTP during electrolysis. So chemical equivalent of a substance is equivalent weight of a substance in grams. For oxygen, equivalent weight is equal to atomic weight upon valency, which is equal to 16 by 2, which we get as 8. Therefore 96,500 coulomb or 1 farad will liberate 1 equivalent of O2. So 1 equivalent of O2 is equal to 8 grams, which is 32 grams is equal to 224 liters. Therefore we get 8 gram is equal to 22.4 into 8 upon 32, which is equal to 5.6 liters, which is, we see our answer matches with option A. Therefore option A is the correct answer. When a current of 3 ampere is passed through an aqueous solution of a palladium salt, the mass of palladium metal deposited in 1 hour is 2.98 grams. If the metal's atomic mass is 106.4, the valency of palladium is, we give 4 options. We have given I equal to 3 amperes, T given as 60 minutes, which is equal to 60 into 60 seconds, where we have W is equal to 2.98 grams. So atomic mass given as 106.4. Therefore we have W is equal to I into T into E upon 96,500, where we get E equal to W into 96,500 upon I into T, which is equal to 2.98 into 96,500 upon 3 into 3,600, which we get equal to 26.63. Therefore valency N is equal to atomic mass upon E, which is equal to 106.4 upon 26.63, which we get approximately, when we solve this, we get 4, which is N is approximately 4, which is our answer matches with option B. Therefore option B is the correct answer. Question 7. The number of molecules of chlorine that will be deposited from molten sodium chloride in 1 minute by current of 300 milliamperes is dash. We give me 4 options. The mass of a chlorine deposited can be calculated according to the Faraday's first law of electrolysis. Therefore we have W is equal to ITE upon 96,500, where we have I equal to 300 milliamp which is equal to 300 into 10 raised to minus 3 amp. We substitute this, we get 300 into 10 raised to minus 3 into 60.35.5 upon 96,500. Where t we have given as 1 minute, which is equal to 60 seconds. We solve this, we get as 6.621 into 10 raised to minus 3 grams. So number of chlorine molecules can be given as which is equal to number of moles into Avogadro number. Which is equal to, we solve this, we get 6.621 into 10 raised to minus 3 into 6.023 into 10 raised to 23 upon 71. When we solve this, we get equal to 5.6 10 raised to 19 molecules, which is, we see our answer matches with option D. Therefore, option D is the correct answer. Question 8. A metal M is known form the fluoride MF2 when 10 ampere of electricity is passed through the molten salt for 330 seconds. 1.950 gram of metal is deposited. The atomic mass of M is given as, we given 4 options. So we have I equal to 10 amp and T is equal to 330 seconds. For W is equal to 1.950 gram, where we have W is equal to ITE upon 96,500, where we get E equal to W into 96,500 upon IT. We substitute the value, we get 1.950 into 96,500 upon 10 into 330, which is equal to, we get as 57.02. So molten salt is MF2. So valency of a fluorine is minus 1 into 2, which is equal to minus 2. So valency of metal given as plus 2. Therefore, E equal to atomic mass upon valency. Therefore, we have E and valency. So we can multiply that, we can get atomic mass is equal to 57.02 into 2, which is approximately equal to 114.0, which is, we see our option D is the correct answer. Question 9. The number of coulombs required to liberate coulombs required to liberate 0.224 chlorine at 0 degree Celsius at 1 atm pressure is, we given 4 options. So for 224 of chlorine at STTP is equivalent to 1 mole of chlorine. So 0.224 of chlorine at STP is equivalent to 0.01 mole of chlorine. In order to deposit 1 mole of chlorine, that is 71 grams, 2 Faraday of electricity is required. So 96,500 coulomb is equivalent to 35.5 grams, which is equivalent to 0.5 moles of chlorine. So that is half moles of chlorine is equivalent to 96,500 coulombs. So 0.01 moles of chlorine is equivalent to 96,500 into 0.01 into 2, which is equal to, which you get as 96.5 into 2 coulomb, which is answer matches option A. Therefore, option A is the correct answer. Question 10. The cost of electricity required to deposit 1 gram of magnesium is 3 rupees. The cost to deposit 8 gram of aluminum is, so for 1 gram it costs rho 3. 1 equivalent of magnesium is equal to 24 by 2, which is equal to 12 grams. So 1 atom of magnesium can give 2 electrons as it is a divalent. So cost to deposit 1 equivalent of magnesium is equal to 12 into 3, that is 36. So the same amount of electricity and hence the same cost will deposit an equivalent of aluminium, that is 27 upon 3, which is equal to 9 grams. So according to the Faraday's second law, for 8 grams of aluminium it costs 8 by 9 into 36, which is equal to rho 32, which is, you see, our answer C, then option C is the correct answer. Question 11. What will be the current required to deposit on the cathode 39.4 grams gold per hour from the solution containing a salt of gold at mass of gold, where atomic mass of gold is given as 197 gram per mole. So we have weight given as 39.4 grams and T is equal to 36, that is 3600 seconds. So for AU3 plus, we have 97 by 3, that is gold, 65.66. So we have W is equal to E upon 6,500 into I into T, which we get I equal to W into 96,500, this is upon E into T. This is equal to, when we substitute the value, we get approximate value, that is 16 amp, which is, we see, answer matches option A. Option A is the correct answer. Question 12. How many hours are required for a current of 3 amp to decomposes electrolytically 1 mole of water? Again, 4 options. We have H2O, that is H2 plus of half of O2. So 18 gram liberates 1 mole of H2. So we have E equal to atomic mass upon valency, which is equal to 1 by 1, equal to 1. So we have Z is equal to 1 by 96,500, where we have I equal to 3 amps and W is equal to 2 grams. So where W is equal to ZIT. So we solve for T, we get W upon ZI, which is 2 upon 1 upon 96,500 into 3, which is equal to 2 into 96,500 upon 3, which is equal to 64,333 seconds, which we get as solving this, we get 17.9 hours, which is approximately equal to 18 hours, which is, we see, our option C is the correct answer. Question 13. Cell 1 containing a solution of mercuric perchlorate, that is Hg ClO4, to cell 2 containing a solution of mercury nitrate, that is HgNO3 2, and cell 3 containing a solution of mercury perchlorate mercury ClO4 are connected in such a way that the same current passes through each of the cells. The amount of mercury deposited will be same in, we're given 4 options. So for cell 1, The mercury perchlorate, that is Hg4O2 as H2 plus, where cell 2 mercury nitrate, that is HgNO3 2 have Hg2 plus. Same for cell 3 mercurous ferrochlorate have Hg2 CiO4 2 just Hg plus. Therefore Hg plus 2 gives 2E to form Hg, and Hg plus E, which gives us Hg. So we have WHG 2 plus ratio of WHG 2 plus ratio of WHG plus, which is equal to S, which is equal to mole ratio of Hg 2 plus mole ratio of Hg plus, which is we get answer as half is to 1, which is we see that cells 1 and cell 2 but more in cell T. Therefore, we see our option B is the correct answer. Question 14. Two electrolytic cells, one containing acidified ferrous sulfate and another containing acidified ferric sulfate, are connected series. The ratio of ion deposited at respective cathodes in the two cells will be dash respectively. So valency of ion and ferric salt is equal to 3. Valency of ion and ferrous salt is equal to 2. So according to the Faraday's second law, W1 upon W2 is equal to equivalent weight of ferrous ions upon equivalent weight of ferric ions, which let X be the atomic mass of ion, which we get as W1 upon W2, that is X by 2 upon X by 3, which we get W1 W2 is equal to 3 by 2. Therefore, the ratio of ion deposited at respective cathode is 3:2, which is answer matches with option D. Therefore, option D is the correct answer. Question 15. An industry produces 40 kg of calcium in 2 hours by electrolysis. How much of aluminum will be produced by the same current in 2 hours? The atomic mass given as calcium is equal to 40 and aluminum is equal to 27. So reaction at cathode, it takes as Ca2 plus of T, which gives us calcium. Equivalent of mass of calcium is equal to 40 upon 2, which is equal to 20. So for aluminium, so the equivalent mass of aluminium is given as 27 by 3, which is equal to 9. So according to Faraday's second law, electrolysis, we have WAL upon WCA equal to EAL upon ECA. So WAL is equal to 40 into 9 upon 2, which we get as 18 kg, which is our answer matches the option D. Therefore, option D is the correct answer. Question 16. For the electrochemical cell of silver, the given equation of electromagnetic cell is given over here. So the overall cell reaction is, we are given 4 options over here. So for at anode, we have Ag, AgCl, solid state, where Cl reacting is a reacting species, metal with sparingly soluble salt, where cathode is Ag, where Ag plus is a reacting species. Metal and metal ion. So at anode, we have Ag solid plus chlorine aqua, which we get Ag chlorine solid plus of electron. And at cathode, we have Ag plus aqueous plus of electron, which gives us Ag solid, where electron get cancelled. So the cell reaction, at total cell reaction, we get as Ag plus plus of Cl minus. This both are aqueous position, which gives us AgCl solid, which is we see our answer matches with option D, that is AgCl, which gives us AgCl as solid. Therefore, option D is the correct answer. Question 17. The lifespan of a Daniell cell is increased by, we're given 4 options. In a Daniell cell, the zinc atoms from the zinc rod lose their valency electron and dissolve as zinc 2 plus. The cations in zinc sulfate solution. So the zinc rod gets depleted as the cell is working. So we conclude that a larger zinc electrode is needed to increase the lifespan of the Daniell cells. So option A is the correct answer. Question 18. The passage of a current in a Daniell cell when copper and zinc electrodes are connected is, we give 4 options. In a Daniell cell, electrons flow from zinc to copper. So through an external circuit, hence the current reverse direction of electrons passes from copper to zinc. I repeat, the current passes from copper to zinc through an external circuit. Passage of current is reversed to the flow of electrons. Therefore, we see copper to zinc go outside the cell. Therefore, we see option copper to zinc outside the cell is a correct answer. That is option C. Question 19. In the Daniell cell, if the concentration of zinc and copper ions are double, then the EMF of the cell is, we have 4 options. Overall cell reaction for a Daniell cell can be given as zinc solid plus copper 2 plus aqua to zinc 2 plus aqua plus of copper solid, where we get E cell, that is standard cell potential, equal to E cell minus 0.592 upon 2 log zinc 2 plus upon copper 2 plus. When both the concentration of zinc plus 2 and copper plus are double, the ratio is zinc 2 plus to copper 2 plus remains unaltered. The EMF of a cell is constant. Therefore, we see option C, that is, it remains same, is the correct answer. Question 20. The hydrogen electrode is dipped in a solution of pH that is equal to 3 at 25 degrees Celsius. The potential of a cell cooled with be the value of 2.303 is 0.059 volt. So we are given 4 options. So for H plus, we need 1 electron, which gives us half of H2. Reducing the potential of hydrogen electrode, we get EH is equal to minus 2.303 RT upon NF log of 1 upon H plus, which is equal to minus 0.59, 0.59 into pH. We know we have pH is equal to minus log of H, that is which is equal to log of 1 upon H plus, which we get as minus 0.059 into 3. Multiplying it, we get minus 0.177 volt, which is, we see, we get option B, which the answer matches option B is the correct answer. Question 21. If the zinc and the copper concentration are 0.1 molar and 10 to minus 9 molar respectively at 25 degrees Celsius, the potential of the cell containing zinc or zinc 2 plus and copper 2 plus electrodes is given. We're given over here. The cell may be represented as zinc the standard potential cell is given as so we have zinc plus copper at the reactant side, and we get product as zinc plus 2 and copper. So the standard potential cell, E cell, that is equal to minus of one n log we substitute all the values which we have, we solve this, we get 0.864 volt, which is, we see our answer matches with option A. Option A is the correct answer. Question 22. The standard oxidation potential of zinc and silver at 20 degrees Celsius are given over here. Which of the following reaction actually takes place? We're given 4 options over here. So given potential or oxidation potential, the reduction potential will be standard potential cell at zinc will be equal to minus 0.76 volt, and for silver will be 0.80 volt. Since the reduction potential of silver is more than the zinc, silver will get reduced and zinc will oxidize. Hence the reaction is, we get as zinc salt plus 2Ag aqueous state will give you zinc at aqueous state with oxidation 2 plus 2Ag of salt. Therefore, we see our answer matches with option A. Therefore, option A is the correct answer. Question 23. The potential of the cell for reaction as given over is 1.5 volt. The standard reduction potential for reaction is given as, we have 4 options. So we have for M giving M2 plus of 2E, where this is going as oxidation. Same for H, it is adding of electron, which gives us H2, which is reduction. So we have N equal to 2. So for the E cell equal to so we substitute the value, we have E cell as 1.5. So if we solve that, we get 1.5 equal to E0 cell minus of 0.0592 by 2 log of 0.1 upon 1. Solve this further, we get E0 cell and standard potential cell, that is 1.5 minus 592 upon 2, which is equal to 1.47 volt. Therefore, we find for cathode and anode. For cathode, we see the value is 0, and for anode, it is M2 plus of M. Therefore, we solve this, we have E0 cell as 1.47. Therefore, value of standard potential of M2 plus or M we get as 1.47 volt. That is, see, we get minus 1.447 volt, which is, we see our answer matches with option B. Therefore, option B is the correct answer. Question 24 for the electrochemical cell given over here. Therefore, we are given 4 options over here. 2 of them are reasons and 2 of them are value of E cell. So we see that EM of M plus is equal to 0.44 volt, and for EX we have minus 0.33 volt. So the standard oxidation potential, this is like standard oxidation potential. So M has a higher standard oxidation potential value, hence it will get oxidized while X will get reduced. So with respect to standard oxidation potential, we have E cell, E oxy at anode, and so E oxy at cathode. For this, substituting the value, we have 0.44 minus 0.33. Solving this, we get 0.77 volt. That is E cell, which is, we see our answer matches option C. Therefore, option C is the correct answer. Question 25, which is the correct nearest equation for the reaction taking place in the following cell? This is given cell over here. We given 4 options over here. So we can write this cell equation in the form of oxidation and reduction. Therefore, an oxidation, we have Mg, which gives us Mg2 plus of 2E, and in reduction, Cl2 plus of 2E is 2Cl, which is this nearest equation, or the final equation can be written as Mg plus of Cl2 gives us Mg2 plus of Cl minus. So the nearest equation can be written as E cell equal to E cell minus of log minus of square Mg2 plus. Therefore, we see our answer matches with option C is a correct answer. Question 26, during charging of a lead storage cell, we give 4 options. During charging of a lead storage cell, electrical energy is supplied to it from an external source, that is the cell function as an electrolytic cell, and the external EMF is greater than the EMF of the cell. So we see that option given as external EMF is greater than the EMF of the cell is a correct answer for this question. So therefore option A is a correct answer. Which of the following is not used as a fuel in a fuel cell? We're given 4 options over here. In a fuel cell, fuel which can be used are hydrogen, hydrocarbon, or any other compound which has high heat of combustion. Hence, nitrogen cannot be used in the fuel cell as it is non-combustible. Therefore, nitrogen is not used as a fuel in a fuel cell. Therefore, option A is a correct answer. Question 28. Lithium, calcium, and potassium metals may be arranged in a decreasing order of the standard oxidation electric potential. Are given four options. According to electrochemical series, decreasing order of the standard electrode potential is calcium, potassium, and lithium. So decreasing order of the standard oxidation electrode potential is lithium, potassium, and calcium, which is we see our answer, that is option D is a correct answer. Question 29. The standard cell potential of given is 1.110 volt. The maximum work obtained by the cell will be, so the maximum work will be done by the given cell using free energy, that is minus delta G equal to N of Fe cell. Therefore, we substitute, we have N as 2, F as 96,500, and E cell is given as 1.1 volt. We solve this, we get 212,300 J. Therefore, we write in kilojoule, we get as 212.30 kilojoule. Therefore, we see our answer matches with option B. Therefore, option B is a correct answer. Question 80. The cell reduction given as over here is represented by, we give four options. So cell reduction given as can be written as in two half cell reaction, which are zinc as a solid form, because of 2E, and for silver where we can multiply throughout the equation with 2. The zinc is oxidized and acts as a negative electrode, whereas silver ions are reduced and act as positive electrode, that is cathode. Hence, the cell representation can be given as zinc to plus Ag plus and Ag, which we see our answer matches with option B. Therefore, option B is a correct answer.